In this third video on gases, we will kind of be finishing up with some more qualitative things and looking at what happens under non-ideal conditions for gases. So the first thing we want to talk about is the distribution of the molecular speed. So the plot that I'm going to show you has the same molecule, the same amount of molecules, and it shows you what happens when you change the temperature. So before we look at the plot, something I wanted to remind you of. We're not really going to do any calculations with the kinetic energy equation, but we can kind of use it to kind of qualitatively understand what's going on. Kinetic energy is equal to 1/2 mv squared, where m is the mass and v is the velocity. Now, if we think back to what we saw in kinetic molecular theory, we saw that when we raise temperature, we increase the kinetic energy. And how's that going to be displayed? Well, we can't change the equation. We can't change the mass. We're dealing with the same molecules. So we're going to see an increase in velocity of this. And this plot shows that. So what this plot on the bottom shows is the distribution of molecular speeds of oxygen molecules at three different temperatures: 300 Kelvin, 600 Kelvin, and 1000 Kelvin. And first thing you want to see is that we're really looking at a distribution. Not all of the molecules are traveling at the same speed. Some are traveling very, very slowly. Our horizontal axis is the velocity in meters per second. Some are traveling much faster at any temperature that we look at. So that's the first thing we want to notice about this, is that we're truly looking at distributions. The other thing that we want to see is that we are, as we're increasing temperatures, increasing the kinetic energy, because it shows up in the velocities. If I look at the blue line at 300 Kelvin, I kind of look at that average or that median, and I kind of mark there. And then I look at that average or that median for red at 500 Kelvin, and then that average or that median that you see for green at 1000, you see that as we increase the temperature, we increase the average speed of the particles. The other thing you want to notice about this is you also kind of increase that maximum speed. Here's kind of that maximum speed you saw at 300 Kelvin. For red, it increased. For green, it increased. So you're seeing an increase in the average kinetic energy as you increase the temperature for that same gas. But remember, we're talking about averages here and a distribution. If you look at any random particle at 300 Kelvin and a random particle at 1000, because there's such a wide range of speeds, there's still a chance that a random particle, if I put a random, I'll make purple here, a random particle at 300 Kelvin that's moving relatively quickly, put an X there, and I pick out another random one, we'll use orange, at 1000, it's still entirely possible, if you're just looking at a single molecule, for the one at the lower temperature to on average be moving faster. That's because it's a wide distribution. So that's why we always want to talk about kind of averages for this. You can't necessarily draw a conclusion looking at a single molecule because there's such a wide range of speeds. But what you do see is the average speed increasing in this. We'll look at another plot, and this plot is another distribution of molecular speeds, but here we're looking at different molecules at the same temperature. So here, because we're at the same temperature, kinetic molecular theory tells us that the kinetic energy will be the same. Okay? Same temperature, same kinetic energy. But because we're looking at different molecules, here we have helium, neon, argon, these are going to have different masses. So if we just kind of look at the mathematical equation, we'll see this on the plot on the bottom. If all three, helium, neon, and argon, have the same kinetic energy, but they have different masses, well, then they better have different velocities. And what you'll notice is mass and velocity is going to be inversely related to each other. The bigger the mass is, the lower the velocity in order to get that same kinetic energy. The smaller the mass, the higher the velocity will need to be to get that same kinetic energy. And you're going to see that in the plot. When you look at the plot, you look at what is the heaviest of these three gases. If you look at the periodic table, the heaviest gas is argon. What's happening with the heaviest gas in green, the argon? That's moving the slowest on average. The lightest gas would be the helium. In blue, that's moving the fastest on average. So what this plot shows is same temperature, same kinetic energy. But if you have different molecules at the same temperature, then what you're going to see is you're going to see them moving at different speeds in order to achieve that same kinetic energy. A couple of terms I want to quickly talk about that a lot of times people kind of get mixed up and confused on. The first of these is effusion. And what effusion is the gradual escape of a gas through a tiny opening from a region of higher pressure to a region of lower pressure. And this diagram kind of shows it. What you see are two different chambers, and they're sealed off from each other in the top picture. We have gas in one and essentially a vacuum in the other. As we turn the valves here, we create a small opening. Once we create that small opening, what we're going to see is that the gas particles are going to escape the region from the high pressure and go into the region of the low pressure until it equilibrates at equal pressures for this. Now, what we're going to, you could do a lot of calculations for this. We're not going to do any of the calculations, but there's some qualitative things we're going to look at. What's going to affect the speed of this process? Well, the faster the particles are moving means the quicker this effusion will take place. So if we think back to the last couple things we just talked about molecular speed, if we increase the temperature, the gas particles will be moving faster, effusion will take place faster. The other thing we can look at is if we can compare a gas with a large molar mass versus a gas with a small molar mass. The gas with the smaller molar mass will be moving faster. Effusion will take place faster for that smaller gas. Another property we want to talk about is diffusion. Diffusion is the gradual mixing of two gases. So diffusion, we're mixing. Here we have the same idea, two different chambers that are sealed off from each other. As we open up the valve, they begin to mix, and they're going to mix until they are completely mixed together. This process of these gases mixing is called diffusion. So just like for effusion, we can talk about the rate that this happens. Well, diffusion, the faster the particles are traveling, the quicker this rate of diffusion is going to be. So how can we get the particles to travel faster? Well, if we increase the temperature, that's going to make everything travel faster. That means that they're going to mix faster. The other thing that this diagram also shows is that smaller gas particles are going to mix faster than the bigger gas particles. Hydrogen weighs a lot less than oxygen. That means if these are at the same temperature, the hydrogen is going to mix in much faster than the oxygen. And you can kind of see this in the second picture here that I kind of boxed in. The hydrogen in green, way more have mixed in with the oxygen than the oxygen has mixed in on the side that was originally hydrogen. That's because the hydrogen is moving faster. It's going to mix in much quicker. Kind of the last thing we want to talk about in our discussions of gases is this idea of non-ideal gas behavior. We've seen for all of our calculations that we've used the ideal gas equation. It's a relatively simple equation. Easy to use, not that many parts. Well, the ideal gas equation only works when gases are behaving ideally. So what does this ideal behavior really mean? Well, gases behave ideally when the assumptions that we made in kinetic molecular theory are valid. If they're not valid, those assumptions, then that gas isn't behaving ideally. So let's kind of go through some of those things we assumed in kinetic molecular theory. We assumed the size of the particles didn't matter. We assumed that we had elastic collisions. We assumed that attractive forces did not matter, that they're so weak we could ignore them. We assume kinetic energy is directly related to the temperature. Well, remember, some of those assumptions don't always work, and I want to show you a couple cases where that doesn't work. Gases are most likely to behave ideally when you're under conditions of high volume and high temperatures. Large volumes, high temperatures. And why is that going to be? Well, let's start with the volume part of it. Remember that one assumption that we made, that the particles, the volume of the particles themselves did not matter. The diagrams on the left kind of show that. So I have 5 particles in each diagram. At the top, I have a big volume. Here, compared to the volume of the big circle that they're in, the volume of these teeny tiny gas particles themselves is insignificant. We can ignore that. But if we take those same 5 particles and start putting them into a much smaller volume, shown below, we may not be able to safely ignore the volume of the particles themselves, in which case we're not going to be behaving very ideally either. So that's why the big volume is kind of important. It spaces the particles out more. The other assumption that we made is we didn't have to worry about attractive forces. Well, attractive forces are there. Remember, kinetic molecular theory kind of ignores them to give you a simpler view. Well, when are you going to have an easier time ignoring the attractive forces? When they're separated by a big space like you see in the top. There's a big distance between these two particles. Those weak attractive forces, we're probably going to be able to ignore those. But in the bottom, when these are really, really close to each other, when they're really, really close to each other, that attraction between the particles, we may not be able to safely ignore that, so we're going to have to figure out a way of dealing with it. You often generally see gases behave more ideally at high temperatures. And for this, what I want you to imagine are 2 gas particles running anti-parallel to each other. So one particle's going left to right, the other one's going right to left. Well, I represent this with big arrows on the top, meaning that they're going pretty fast. If they're going pretty fast, they're going to zoom right past each other. They're not going to spend a lot of time near each other. But in the bottom set of pictures, I kind of circled down here, the particles aren't moving that fast, even if they're still running anti-parallel to each other, one going left to right, one going right to left. What you're going to see is they're spending more time in close proximity to each other. Well, that's going to affect their trajectories, their paths. So high temperatures are going to help gases behave more ideally as well, along with the large volumes. Those 2 conditions make those assumptions we made in kinetic molecular theory a little bit more valid. So we have ways of dealing with this non-ideal behavior. There's another equation we can use. It's called the van der Waals equation. Remember, in the ideal gas equation, it treats kinetic molecular theory as true. All the assumptions work. And that means we can treat all the gases as the same. Remember when we did the calculations, it didn't matter what gas particle we had, whether it was CO2, whether it was H2S, whether it was H2, and all those calculations we did, it just didn't matter because we didn't have to worry about the size of the particles, we didn't have to worry about attractive forces, everything was identical. But when the kinetic molecular theory assumptions aren't valid, we can't use the ideal gas equation. It's not going to work. So there's another equation we can use. It's called the van der Waals equation. The van der Waals equation is more complicated than the ideal gas equation. You can see it here. It involves correction terms and is specific for each individual gas. Now, I'm not going to ask you to do any calculations for using the van der Waals equation, but you should qualitatively understand what's happening in terms of this van der Waals equation and what those correction terms are and kind of what they're doing. First thing I kind of want to show you is if I kind of block out these correction terms, I kind of remove them, what does it look like? Well, it looks just like the ideal gas equation, PV equals nRT, if I kind of don't have them in there. So these are correction terms for that. Well, let's talk about that large volume. That large volume plays a really big role in kind of having to decide whether you need to use the van der Waals equation or if you can get by with the ideal gas equation. What's going to happen if the volume is very, very large? Well, if the volume is very, very large, look at this correction term. This correction term here, if the volume is very, very large, so if the volume is very, very large, what's going to happen is if the volume's large, look, it's in the denominator and it's squared. If this volume is very, very large, what's this whole correction term going to be? It's going to be very, very small. If you got a large number in the denominator and you square it, well, then that entire number is going to be very, very small. If it's very, very small, then you don't have to worry about it because it's going to look like zero. It's going to look like back what we had with the ideal gas equation. Likewise, this other correction term, V minus NB, if the volume is very, very large, then subtracting something very, very small from it isn't going to change the value any. You would be back at not having to worry about it, and you'd be back at the ideal gas equation. That's why that large volume is so important. That large volume gets you back from the van der Waals equation to that much easier to use ideal gas equation. So let's talk a little bit about that. So you saw how the big volume makes these terms start to approach zero, which means you can kind of ignore them. You don't have to worry about them. They're not going to be a significant factor in that. Let's talk a little bit about the A and the B terms here. A deals with the attractive forces for a specific gas. A molecule that has more attractive forces will have a larger value of A. So that's what the A is representing. It's specific for a gas. Nitrogen gas is going to have a different A value than carbon dioxide gas, which will have a different A value than oxygen gas, which will have a different A value than neon gas. Everything's specific for that because we're taking into account those attractive forces. The B deals with the volume of the particles themselves. Particles with a larger volume will have a larger value for B. So if you look at the B values, they're going to be different depending upon what gas particle you're actually dealing with. The larger the particle is, the larger the B value will be. The smaller the gas particle is, the smaller that B value will be. So the van der Waals equation takes those things into account. And There are some extreme situations where even this van der Waals equation doesn't work, and you'd have to use an even more complicated equation that has even more correction factors and more terms and more things to consider. We're not going to worry about the calculations for this. That's just mathematical busy work. But what we do want to do is recognize why we need the van der Waals equation or other equations besides the ideal gas equation, and what those parts of the equation are doing for us in relating from ideal gas behavior to non-ideal gas behavior.